I'm Mary Thomas. I lead the HPC training. I have a background in physics and ocean modeling and love everything HPC. So with that, I'll go into screen share mode and make sure everybody can you see the right view of the presentation?
Yes.
Okay, great. And I'll get this out of my way. All right, so with that, we'll move forward. So the complex project stands for Comprehensive Learning for End Users to Effectively Utilize Cyber Infrastructure. And this is a new program that we've been running from the beginning of this year. And the idea is to cover what we call non-programming skills. And what we mean by that is not that you don't program at all, but you're not programming in the parallel computing MPI environment. That would be a little more advanced level of training. The idea is to bring in people like you who are working on advanced research that is at a stage where it needs to run on a supercomputer and teach you how to run and operate in that complicated supercomputing environment. So we cover all the basics you might need to upload your files, install and compile maybe, or use an already installed application like Amber, and then move on and get your jobs done and download your jobs, run them on the supercomputer. So today we're going to talk about interactive high performance computing, and this is interesting to us, and it's an emerging, evolving field, but the idea is, how do you use a supercomputer? How do you run jobs? And we have webinars on batch computing, and that's one way, but interactive is where you're actually logging on and you have access to that supercomputing node to do things like visualization. So we'll talk about that today. And so how to interact with them, and then some examples of what we mean by interactive computing. So get this on the screen. All right, so you can do an awful lot with supercomputers. They're very powerful, and some of it you see all the time, like ocean modeling, weather modeling, climate modeling, and then astronomy, astronomy modeling. Just there's a whole lot of applications, and supercomputers are very impactful. Like for COVID modeling during the time of COVID, we dedicated all the supercomputers to pretty much to running chemistry computations for them to find a good vaccine. So there's a lot that can be done, but they're very powerful and can enhance your research, but it takes some skills to understand them. So the good news is you have a model that's growing and requires that you get onto a machine like Expanse or other parallel computers. The bad news is it is challenging. So somewhere on your laptop or on another machine, and you need to get access to these supercomputer nodes. And they're pretty complicated, and it's if when you have thousands of them available, like on Expanse, hundreds of nodes with thousands of devices on them, it's pretty complicated, and we use systems to help simplify that scheduling and tracking and recording the I/O from everything. And so we'll talk about job scheduling and job scaling, one core to thousands of nodes. And then for large jobs, these schedulers are required, and they make a big difference for you once you learn how to use them. So this is a Expanse, which is a modest scale system compared to El Capitan with hundreds of racks and a petascale, exascale systems. Expanse is a petascale system, but we have 13 plus racks, and each compute rack is designed to incorporate CPU computing and GPU computing. So it's a mixture. The idea is that most of the jobs that Expanse is designed for are medium scale because most people are working in that range. So we try to optimize the architecture for things that can run on one rack and maybe multiple racks, but ideally one to two racks. And then if your model is getting so big, then you might move to a larger system, and we can help you with that. We can help you figure out where your job will run best. So we've also got, all kinds of petabyte scale storage and growing. This is an older diagram, so we do have more racks and we do have more storage. But you have to handle the data and use a custom data management system. And I think Marty will be talking about that in 2 weeks. And so when you have terabytes of data being generated by your model, handling that data, like where do you store it? You can store it with our Expanse Luster file system, but at some point you may need to move it somewhere else to analyze. So how to handle and manage your data is as challenging at times as running your computation. And then we have an advanced networking system that is really all over the United States. And I won't go into too much detail, but there are some links in my talk that give you a little more information. So jobs can be run as batch on HPC systems or interactively, which is what we'll talk about. We've already had webinars this year on batch computing, but I'll take a moment to kind of highlight what batch computing is all about, and we'll talk about that. So these are just some cartoon scenarios for ways people are running jobs and how they end up running and benefit from a batch scheduler, which is, in this example, this is the Torque Resource Manager. You have many allocate queues in the scheduling system and lots of jobs that want to run. And it's up to the scheduler to take, if you were to log on to Expanse right now, you would see 1,500 jobs that are running right now and 15 to 2,000 pending and waiting for their turn to run. So the scheduler's job is to optimize and make the running of these jobs more efficient and quicker turnaround for you. So this shows a person at their workstation and they're running a simulation. The simulation runs, they get their results back. And that's basically how the batch system works. You turn it over to the batch queue. It gets all the I/O from your application, stores it, and gives it to you in an output file, which you can name. Another way is to run applications that are running on Expanse in parallel in the background. And we have a portal for that, portal.expanse.edu, and it's got R, it has MATLAB, you can run Jupyter notebooks through it. It's really, if you can find a way to make that system work for you, it saves you a lot of time and effort, and we'll talk briefly about that later on. And then you can run notebooks through Jupyter Hub servers, for example. We don't do that on Expanse because of security model that we support, but you can, and I'll talk about ways to launch a Jupyter notebook on Expanse and have access to an interactive node that way. So what's batch computing? Let's just take a moment to talk about that. On any HPC type system, we have to share these resources. We have all those nodes, we have all those cores available, and we want to make sure everybody has access, and we don't waste time in compute time. So the batch job is, the batch scheduler helps you do that. And once you get used to using it, it's really like you write a Unix script, and we have tutorials that talk about how to use Linux and write scripts. And the script just has some keywords defined in it, and then you submit it using a command from the command line, and your job will get submitted. The queuing system will evaluate your script and make sure it's in good shape, and then get it pending and into the queue and waiting for the chance to run. So the scheduler allocates these resources. Typically there's different queues, and these are logical decompositions of the nodes that are on the machine. Like one might be, if you want a quick turnaround, you'll use more of your allocation for it. Another one might be the debug queue, which is 30-minute limit, but you can get a job running pretty quickly just to test and debug a small. And you might also choose a queue that specifically runs on CPU, specifically runs on GPU. So there's all kinds of ways to run jobs. So we have different queues for that. And then there's partitions are also the job queues, and we can configure them for particular kinds of job. So you need to understand batch jobs. I'll briefly touch on them today, but like I said, we have a webinar on that if you want to look at that. So the main goals would be to minimize the time between when a job is submitted and when it's done. so that you don't have to wait 2 weeks. You hopefully can get a quick turnaround. Optimize the utilization of the CPU and the GPU, so that we have optimization there. Maximize job throughput, manage as many jobs per unit time as we can, and support running these jobs automatically in the background. So, often you can submit your job and most of the time go get your cup of coffee, hopefully come back and it's done, or a week later it's done depending on your job. And then it does a really important task of finalizing your job. All the I/O, like your print statements, you're saving data to a file, locating where that file is. You can finish your job and move files and stage them. That all gets done at the end, and it can take a while for that job to get finalized. So your job your running executable might be done, but it may take several minutes for the queuing system to clean things up, gather all your data, move it to wherever you've defined it should go, get the environment information that you wanted to capture, all your I/O, or capture any errors that you might want to see. So that part is really important. At the end of the day, you get an output file that you can define the name of and the location of where you want it to go. So the batch does an awful lot for you. So here, this little cartoon shows you logging into the front end nodes where you don't run jobs on the front end node. Those are just for people to get on the system, set up their job, maybe compile it, check and make sure their batch scripts are working. Then they submit the script to the scheduler. The scheduler gets it submitted. Eventually it runs, and then you get data back out of it. You don't run jobs interactively through the batch scheduler unless you have a particular request to use an interactive node, and we'll talk about that. This is another overview of Slurm, which is what we use, the simple Linux utility for Resource Manager. If you're familiar with Futurama, yes, they did name it after Slurm, or they found that Slurm worked for an acronym. And they used to hand out cans of Slurm at our annual meeting, and it was really pretty bad tasting. So there's a little joke there, but it does show you that same cartoon I showed you before, but the Slurm Resource Manager runs on a service between the head node where you're logged in and the remote nodes. And you have several commands that you can control what you're doing. You can look to see SQ, how many jobs are in the queue. You can submit using SBatch. You can also use SRun to interactively run jobs. And then there's several other commands that you might want to use. And they're all allowing you to interact with the Slurp scheduler. And again, I refer you to our complex presentation on batch computing. This is sort of conceptually what's going on, and this shows over time you have all these jobs that are running and different nodes. And here you have one big job that's taking up 4 nodes, and it's taking a long time. And behind it are jobs that are waiting. So the scheduler kind of maps out how to fill this timeline and these nodes with jobs. It has an estimate of how long it thinks the job will take, and you're required to put in a number close to that estimate, a time limit. So it schedules jobs around its knowledge. This is pretty, simple for just 6 nodes, but when you have, thousands of nodes, it becomes really complicated and interesting. So the number of jobs that get submitted affect the scheduling, the runtime, the number of cores that you might need, the memory that you might need, what accelerators you're using, and the libraries. So it plays this game in this presentation, multi-dimensional Tetris. You can learn more about that at this HPC Wiki site. So next we'll start talking about what's interactive computing. And why do we need it for high performance computing? We didn't used to think that we would want it or need it or could possibly use it, but over time it's evolved. So in computer science, I'm doing interactive computing right now. You're doing interactive computing from a pure computer science hardware design. You're running your laptop, you're hitting keys on the keyboard. I hit a keyboard input to change the slide. That's interactive computing at a very simple level. So you guys actually do it all day long. software that you run to interact with a computer. So what differentiates interactive HPC computer and regular, having access to computer hardware is this real-time ability, the ability to real-time work with a very high-end supercomputing node or set of cores. And you get to be on it, log on to it, and you can type onto it and run applications that you normally couldn't run on just a small laptop or a small machine. And so this has opened up the door for a lot of visual applications and the ability to analyze your data. Imagine your job is generating terabytes of data, and then you want to look at the data. Well, you just might need to get an interactive node just to go look and maybe visualize your data, run an application to visualize it. So these are becoming very relevant these days. So you would use it for code development. Sometimes larger applications might take hours to compile. So you would, if you do it on an interactive node, you can do it a lot more quickly. Real-time data exploration, large data sets, like I said, and then it might need inputs like notebooks, MATLAB, RStudio. And then these are the results of your user input and output. So this sort of shows how Slurm would get you an interactive node. You would send a request into the Slurm scheduler and tell it, well, I need a one or two or some number of interactive nodes to run this particular application. And Slurm will launch the job for you, but then return or even move you onto that node. And we have an application called Galileo that runs Jupyter Notebooks that's exactly what happens. So you would need it or want to use it for when you need more memory and your job doesn't fit onto the CPU system that you've been using. And these numbers are current. They were current at the time, but they've probably changed a little bit. We're always adding more to Expanse. You have too much data. Your application needs more room, and your network is probably too slow. So you can have really high-speed connections to in the interconnection network on Expanse is high speed. Different kinds of applications and methods are interactive on a high performance computing node. You can interact with your data, and I'll show you some examples about this using Unix commands, just looking at the file information and grepping. Still, if you have a lot of data and you need to grep or do awk or some simple Unix command on a very large data set, it might go faster on an interactive node. You can look at the file contents of these large data files. And you can use data browsers like NetCDF, and there's other advanced data storage compression schemes where they take the ASCII data and compress it down into some kind of binary format, but then you need applications to look at the data. And so you could do that on an interactive node. And you might want to plot some results from the interactive node. And some of these applications allow you to do that, like GNU-plot or MATLAB. And then these data visualization applications, NetCDF, HPS, that's HPF is for a file format. Tau is a visualization analysis system, ParaView, and there's others. And then there's analysis platforms like MATLAB and R. And so these are just some cartoon diagrams of some of the applications that we consider interactive, especially Jupyter Notebooks. They're incredibly useful and are pretty much a de facto standard for almost everybody doing scientific computing because they're so flexible and powerful. That doesn't mean you wouldn't need something like MATLAB here. This is a Jupyter Notebook, or ParaView or something like that. And ParaView is somewhat complicated, and we support it on Expanse and other SDS systems, but it's very advanced. But you can do interactive 3D visualization of your terascale data. The Expanse user portal, we have a portal that is a website that allows you to access Expanse. You can log into the portal. Anybody you log in with your Access ID or your Expanse ID, and then you get mapped onto this portal. the idea is to have applications and simplify your interactions with Expanse. And so when you launch it, and I'll show you more examples, you can get a status of the notebook getting ready and mapped to a node and then running, and then you can access your local files on Expanse. And there's other things that you can do with the portal. And if we have time at the end of the day, we can try and get you guys logged on if you haven't used the portal. It can really simplify your interactions with Expanse, especially if you don't really need require command line, like you're just going to run R, or you're just going to run MATLAB, or you're just going to launch a notebook. Then these would be this is a good environment for you. And when you get these interactive services, we want to give you a caution, which is they provide access to the file systems, and by default with Jupyter out of Anaconda, for example, it's often over HTTP. And so we've done a lot of work to fix that security vulnerability. So we need to make sure that any hardware, any software applications we've got, like Portals, Jupyter Hub, and other services are not mounted directly onto our login disks, our login nodes, because the security vulnerabilities are just too strong. And so we don't allow applications to run on the login nodes. You might try, but that job will get killed. Get an interactive node, run your application. I'll talk a little more about that. So how do we access interactive HPC nodes, and then what can we do on them? So to launch them, like I said, you may want to launch MATLAB or notebooks. You may need to stage data, AI applications more and more, PyTorch, TensorFlow. They're dominating a lot of compute activities right now, or you might have a very large application to compile. So these are two examples of getting a CPU interactive node or a GPU. I tested them yesterday. They all worked. You run these, you log on to Expanse, you run this command, and in this one we're just trying to get onto what's called the debug queue because it's faster, not much memory, just a few tasks per node, and it's just a demo to show you how to get that going. And then what you do on the node is up to you. We're not launching an application, we're using the Galileo SRun on this one, and then we can launch our notebooks. The best way is using Galileo. But this is if you just need to get right onto the node. Okay, so using the interactive node, I need to keep moving through the talk, make sure I stay on time. So this is just an example. The code here is running MPI Prime. We have example notebooks, and we have a repository full of example applications that you can download and clone and install. And we also keep a lot of application information in a location on Expanse, and I think I have it in one of the slides coming up, but it's in like /cm share, and Marty or Bob, perhaps you could put that in the chat for people. But we do have a place where there's all kinds of applications that have been tested and vetted and maintained by our user support group. They not only install all the libraries that you might need for the module environment, they install and test applications and make those available to you guys. So this one is getting a GPU node. It works just the same way. And I just always include this example of when you're on the node, run NVIDIA-SMI, making sure you have the right modular environment. And if that answers, comes back with this kind of data, then you know you're on a GPU node. So now we move to talking about some visualization applications. Like in this one here, we have, I think, X11 forwarding, right? Okay, so sorry, one of the Zoom images was over my label. So X11 forwarding is a way that you can connect a laptop, a local device, to remote systems and forward not only the text, but the imagery and information like that. Mac OS uses Quartz, and then on PCs there's other applications. But the idea is that you're down here on your workstation. You have a keyboard, a mouse, and a screen, and you type and you move things around. This X server is a service that then takes that data and forwards it to the remote machine where you're trying to do things like launching MATLAB on the remote machine. And as long as everything works, it's great, and you can get it running, but sometimes it doesn't work as well as we'd like. And the Mac OS systems from Ventura on, they do have an X11 problem that they should debug, but they aren't. That said, every now and then I can get it to work, so I'll show you some working examples, but I won't guarantee that they work tomorrow. They worked the last time I tested them, so we're recommending that in the event of an application you want to run, see if it's on the Expanse portal, so all of that X11 forwarding is taken care of for you, or see if we can get it installed and supported for you. But to access and activate X11, you can use the -Y in your SSH login command. And that just sets up that server and gets it involved in your communications. So if you want to get to running a visualization application on your interactive node, you have to do a little bit of work. And I'll just put this in here. Again, if you can use the portal and run stuff from there, I would recommend it. So you basically end up creating two terminal windows. You have to log on to Expanse first of all. In window 1, you get the interactive node. You know you've gotten an interactive node with this command. That's from my examples. When all of a sudden the node that you're on changes to something like Expanse 955, then you know you're on the login node. And that means you have permission to log in directly to this node. So you log on to Expanse in window 2, you SSH-Y forwarding that Xterm connection to the remote machine, make sure your modules are correct, and then try to launch MATLAB. The big problem with this is it's very slow. It's slow with a capital SLOW. And so it's not that you can't get it to work, but things time out, and you go through a lot of networks trying to make this work, which again, if you can run something on the portal, do or request that they integrate your application into the portal if possible. So that just makes an example of how to do it, and then it's up to you to figure out what you want to do. So now we have time and space to go through a few examples of how to use doing X11. One of the oldest plotting commands in the programming universe is called GNU plot, and more is getting replaced by programming languages like Python and C and C++. They have their own plotting libraries, so it's not as often used, but it's used. You can use it a little bit. It does require that Xterm X11 forwarding works. I was able to get it the last time with this Xquartz issue on Mac to run. You can run it from the command line and do things on the command line, but I was able to plot a sine X curve in black and white. Normally you would get color by default. So it's very limited right now, and I would recommend you look at other plotting analysis, like if you have to incorporate something into your application. A more advanced and complex program system, I mentioned the NetCDF and binary compressed file formats for data from very large output files, and this is an older format, but it runs. I got it to run on Expanse, and you can launch and mine your data. You have to install it locally for yourself, or it may be installed at this point. I'm trying to distinguish the two cases. So you can take your data and look at it, but it's not easy to read. It's in binary format, so you need to use something from the NetCDF library. So you can. I do have an example in here that you can install. You have to set up your modules right. You have to configure environment variables and compile what you want to look at, what commands you want to run, and then you could look at your data. So here's how I did it for setting things up in a .bash profile. In the binaries, you'll notice the binaries are installed. See that long path here? CM shared apps SPAC CPU ops SPAC Linux. That is the one of the installations. Whoops, let's go back up. That is where our amazing user support team and operating systems people install all the software. So you can go to /cm shared and see everything that they've installed. And that means, if you're using a different version of SPAC, then you would have a different Linux installation. So they've taken care of all of that for you, including, netcdf binaries. So here I'm loading the modules that get me connected to netcdf. And then to find out, well, is it working, there's a command called ncdump, and it will take that binary data and print it all out in ASCII form, which is human readable. And so ncdump is in my path. You can see it's a really long path, but it's there. And ncview is a visualization application. So here's an example of some data that I'm generating and compiling and running, and it's making a data.nc file. And so if I look for ncdump is how I would view it. There's a lot of options, but the simplest view is to just ncdump the simple, and I've cut it down so that it's not showing everything, but there's a lot of information in a compressed file that motivates you to use it. Besides ASCII, you can have it store all the variables and configuration data, the dimensions and names of your matrices, any data that you might want to be stored along with your compute results. Using a compressed file format like this is really worth the effort. And again, there's netcdf, there's hdf, there's a couple of other formats out there. A little bit of work learning it, but then all the variables that you use for that one computation are in that output file. So recovering and analyzing it really helps with post-processing. Okay, so again, here I'm printing out the data. You can see it's printing out all the values for the density, and SNP means it was a lot more data than that. And you can visualize, I was able to get enough bandwidth for enough time for this to not time out, that I was able to just use something called NCView my data, and it gave me a density plot right away. So this ability to be on an interactive node and have software run for you and analyze your bigger files is very valuable. Again, with this launching an interactive visualization program from your house through all these connections to an interactive node, the latency can sometimes be really frustrating. So again, the portal's optimizing things for you, so you might consider the portal. Okay, so if you are in a situation where you have netcdf data and you need help getting the visualization, reach out to consult@sdsc.edu, and the support group will try and help you solve your problems. So there are programming and visualization platforms. We support MATLAB from the command line, but it does not. The Xterm forwarding, X11 forwarding didn't work very well for me the last time, but I did include this example for those of you who want to try it on a different system. It works the same way or quite similarly, but I recommend use the Expanse portal for MATLAB. It's just the simplest way. You can see obviously this is fun to dig in and play with all the connections and X terminal windows and stuff, but it's really complicated. And we've got it on the portal, so consider using the portal if you can. And this is what it looks like when you're getting MATLAB to run. Anyway, for GUIs, use the Expanse portal. Same thing with R. TSCC supports R from the command line, but we have R installed on the Expanse portal. We don't support it from the command line. Jupyter Notebooks, we do support running Jupyter Notebooks from interactive nodes, and I'll talk about that. But Jupyter, of course, I don't need to explain it and define it like I used to have to. Everybody is working with notebooks, and if you aren't, that's okay too, but it's a very convenient way to interact with your computational work. And if you need to change the dimensions of an array, you can do it in a Python environment. Actually, there is Jupyter notebooks that support C and Fortran. I just think the Python environment is pretty much ubiquitous, and most people are using that. But the Python commands could execute a Fortran submodule, for example, if you had Fortran code. So don't think that you can't do your application. You might have to do some porting. Okay, so to run them securely, by default, and I'll show you a couple of diagrams, by default, when you launch a Jupyter notebook on Expanse using either you've installed your own Anaconda environment or you're using the Jupyter command that's by default installed on Expanse, when you launch it, the default is HTTP. It is not secure. And we don't recommend that, and we don't want that, so we try to prevent that. And so we've put a lot of work into a new environment and a new way of launching the notebooks where you're guaranteed an HTTPS connection. And so I'll talk about that. We have this internal on our cluster, this satellite reverse proxy service that builds connections for you and gives you a virtual connection, and you launch and access this with the Galileo client, and I'll show you examples. So that allows you to securely launch your connection. But even if you have the HTTPS connection, remember that URL that you get for that Jupyter notebook, it's like a password, because Jupyter notebooks are able to navigate file systems. We try to limit and have good sandboxing of your account, and your file system, but still people are clever. So if you're in a public area and you're launching your notebook and you go, oh, I'm all secure, I have HTTPS, and you walk away, somebody could step in and access your local files. Most of the time when you do get hacked, it's limited to just that person who got hacked, because we have sandboxes around everybody's environment. But again, hackers are clever, as we all know. So the best thing is, close your notebook. You can, put the notebook to sleep if you have to walk away, or just shut down your notebook server, so that and when you are done with the notebook, remember to shut it down so you don't use up your allocations. If you say, I want a notebook running for 2 hours and you only need it for 15 minutes and you don't shut it down, you'll still get charged for that full time. Okay, so the reverse proxy service is internal to the network, and it allows us to launch jobs for you using a back-end queuing system. It helps create a connection between your web browser and a node on Expanse. And the notebooks are hosted on this internal cluster network, and then you're able to access it through the HTTPS connection. All right, so Galileo is a shell utility that is maintained by Marty, who is here. He's done a great job generalizing this and adding more and more features to it. But you run that from the command line on Expanse, the login node. And that's all you need to do. It's very simple. You need to set up one environment variable. And it was, and it's part of, used in the back end of the Expanse portal as well. So it gives you a HTTPS URL with wonky naming on it for security, and it supports containers. You don't have to install a Conda environment unless you want to do really specific things like specifying other special variables. There's a lot of arguments you can pass to Galileo. As it generates and builds the batch job script for you, submits it for you, logs the batch script information, and gives you that URL, and then you go to a waiting page while you watch the job get built out and submitted, and the node gets assigned. It does so much, it's just great. So if you're in a position where the portal's not quite right for you, then you would run using Galileo. So here's like a cartoon diagram. There's a lot going on here, but basically you SSH onto a login node on Expanse, which is SSH, so that connection is secure and encrypted. What people don't realize happens is if they were to launch a notebook and enter it into a browser, that notebook connection that you might try to run on the login node, that's HTTP. Even though this SSH connection is encrypted, by default, it's not encrypted. So what we do is we require that you run Galileo, which internally the reverse proxy service will talk to the Slurm scheduler, identify a node for you. Internally, it's HTTP, but it's inside behind a firewall. What you get back is a wonky URL that connects to the SRPS, the Satellite Reverse Proxy Service, and you have a secure web browser connection. And it's very popular, very efficient. It's a real connection to that node, and you're running your notebook on that interactive node. And this is just an example. Here's the command for Galileo. You have to make sure you've got the right path set up so you can see Galileo, and it has a lot of arguments. And like I said, Marty is here, and he's the one who developed it. It launches, and when you're done, you'll get, when you enter this URL that you get when you first request the interactive node and the Jupyter Notebook, you'll be redirected to a pending page, and you can watch the stages. Eventually, all these stages are completed, and this means, you know, where you're in the queue, and that takes some time to get your job processed. The server has to make sure everything in your request script is good, and if you get that green ball, then you know you're in the queue. My batch script worked. Sometimes you have typos like the wrong account number and things like that, and that means that would end up in it being rejected. And then it starts to run, it gets mapped to a node, and then it's all ready to go, and up will pop your Jupyter Notebook with the ability for you to read your files on the Expanse system, for example, on an interactive node. Now you can start running your code. And we have examples of, you know, working notebooks if you need them to get started. We have a collection of Expanse notebooks. I'll show you the link that we've just got done testing and updating for you to, down to Hello World. So Hello World's always important. It's one of my lectures I give everybody, which is make sure you have something that's the Hello World equivalent for whatever you're trying to do, because when you get on and all of a sudden your code's not working, you may have made a change, you may have made a mistake, but it may be that the system's down or something in the system's not working. There's so many layers of complexity, especially when you first start, that if you can get like your Hello World notebook to work, all that stuff you needed to have right up to that point, okay, it's good. Hello World works. That means most likely you made a code change that's causing a bug. So having a Hello World is really a helpful thing to have. All right, here's the Galileo client with all the different arguments. Make sure you put the right account in there and the partition that you want, and then the rest of this is just up to your code examples, what you need to do for your code. And then here's an example of actually using it. You have to make sure that Galileo is in the path. You can put, if you do a lot of work with Galileo and notebooks, put that into your bash file or whatever environment you're using, that so that it would get set every time you log on. And then here's an example, account ABC123. That's not a real account, so use the one that you have an allocation for. And then here we're loading in some environment modules. So this example here should work for you if you get the right account. So you get the normal Jupyter information and the notebook session. You get this this URL. And again, when you first put this URL in, you'll get that pending page that will tell you the state of launching the notebook. It takes a little while. And then once your notebook comes up, you can do your work. Here's an example of it. It's almost ready to run, but not quite. You can also, if it's taking a really long time to launch, like you're in this pending queue, you can get the job ID, which you get that when you launch your notebook, and take a look at it and see what's happening. Is it running or is it not? And same thing for GPU. It's identical. You can run a notebook on a GPU node. And these words here, in the URL, these are generated randomly from a word dictionary to get unique combinations that are hard to predict. Okay, so there we know where our notebook is running on a GPU device because the NMI command works. NVIDIA SMI, excuse me. And here's our notebook examples. This is the collection that we just organized, and we've tested them. They all worked for us. So if you find that they don't work for you, but you can also have different views. This is just by name, but you could look at them sorted by CPU, GPU, or are they serial or parallel. And we have some AI examples. We have Hello World. We have some that use different Numba, Pi, different modules. And for each one of these notebooks, we tell you the requirements, what modules that notebook needs. We let you see that. So and we also have it in this column here. So if you're having trouble getting one of these working, reach out to Consult and make sure your environments are set up correctly. And if you find that there are issues, be sure to send a ticket to Consult and let me know so we can keep these running well. And at the end, I'll try to put that link into the chat. Okay, so we're getting to gateways and portals and getting towards the end of the talk, which is perfect. Here's the Expanse user portal. I tried to log in and I got logged in, and so sometimes it's a little kludgy depending on which identity you use. And so hopefully you guys have been able to log into the portal with your portal ID and get in and take a look at the different applications that we've got. You can also just look at the Linux environment. You can go right in and look at it from the command line environment. It's very powerful. You can build jobs, submit jobs, and there is a help guide right there for you to download, and I suggest you download it. It's got a lot of valuable information. And again, if things aren't right, consult at sdsc.edu is there to help you. So here we're looking at a list of files. And you can also, like I said, look in the terminal shell environment, and you'll see the same thing. Just if you don't like the shell and you're more familiar with the GUI interface, that's what it's great for, is what you are comfortable with. Our goal is to make it easier for you to run jobs. Here's how you set up MATLAB. You do need a few things like what partition you want to be on, how many hours you think you want to run it. There are some fields to fill out. These examples in here should work for you, except the account. You need it for it to be your allocation account. And then once it launches, you can monitor it pending, and when it's ready, you'll see that your request is running, and then you can go in and plot SINX or whatever you want to do. Same thing for notebooks. There is a field for running a Jupyter session, and I've taken the liberty of setting up, again, an example. You can cut and paste right from this. You do want to, use the right Singularity file. So these are just what I'm recommending. They work for me as an example. You may need a different Singularity container, and you can take a look at what's in this CM Shared Apps directory, or interact with consult at sdsc.edu to see if there's a different container or you need a new container, or your container's not working. Okay, so that is for launching a notebook, and I think we're at the Q&A. So I will stop sharing and see if there's any questions or anything else people need to know. Thank you for your time.